Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. In the last couple of lectures of ECE2026, Introduction to Signal Processing, we've looked at frequency responses of discrete time systems. In this lecture, we'll talk about how such discrete time systems can be used to process continuous time signals. Now, I've titled this lecture Digital Filtering of Analog Signals, but it would probably be more accurate to call it discrete time filtering of continuous time signals, since there's nothing in the theory I'm about to describe that actually requires these signals to be quantized in amplitude. But this title isn't as catchy as this title, and in practice you'll most likely be implementing these kinds of schemes on a digital computer. In our study of linear and time invariant systems, we discussed how you could put an impulse delta into the system and get out an impulse response H, and this impulse response H completely characterizes the system. We also talked about the idea of a frequency response. If you put a complex sinusoid into the system, you get the same complex sinusoid out, multiplied by a complex number. That complex number, capital H, is the frequency response, and it's a function of the frequency going in. And you can find the frequency response from the impulse response using this formula. Here we've written it with n going from minus infinity to infinity because this idea applies to all LTI systems, not just FIR filters. Now I'm oversimplifying things here a bit. There are some conditions on little h that need to hold for big H to be properly defined, but we'll talk about those later. Since n is an integer, the frequency response is periodic with period 2 pi. In the last lecture, we saw that if we put a cosine into the system with frequency omega naught hat, amplitude A, and phase phi, then we get a cosine out that has the same frequency. For the amplitude, we multiply that by the magnitude of the frequency response evaluated at the frequency going in. And for the phase, we add to it the angle of the frequency response evaluated at the frequency going in. This is the frequency response of an 11-point averager. We'll talk about what this is in detail later. The main point I want to make right now is it does have this 2 pi periodicity, so we will mostly focus on this region here between minus pi and pi. And this is the region that we'll talk about when we use terms like low-pass filter or high-pass filter. This would be considered a low-pass kind of response, and you shouldn't be tempted to look at this up here and think of it as a high-pass filter or a band-pass filter. Just look in here. So the last several lectures have focused on going from x of n to y of n. They focus just on this bit in the middle. Some of the earlier lectures talked about sampling and reconstruction. Now, I'm using the term A to D and D to A. That's analog to digital and digital to analog. But again, there's nothing in any of the theory that we're using that actually requires us to digitize things in amplitude. So to be more precise, we could say continuous to discrete converter and discrete to continuous converter. But in real life, you're probably implementing it like this. This lecture is about tracking spectral components as they work their way through the system. We start with the spectrum of x of t. We digitize that signal to get a discrete time spectrum. So we go from omega land to omega hat land. We're putting on the hat. And we like to design our system so that aliasing isn't a problem. So you'll often have an analog filter sitting in front that filters out frequencies above the Nyquist frequency of the system. Remember, the Nyquist frequency is half the sample rate. Keeping the hat on for a moment, we see what the frequency response big H e to the j omega hat does to these spectral lines. Some of them may be boosted, some of them may be attenuated, some of them may have the same amplitude and just have their phase changed, and some might be killed altogether. Now, all of our examples for now are for finite impulse response filters, but this idea also applies to the infinite impulse response filters we'll look at later. And then we take the hat off, going from omega hat land to omega land, going back to the continuous time domain. Assuming we don't have to worry about aliasing, when we enter the computer and put on the hat, we divide by the sampling rate. And then when we leave the computer and we take the hat back off, we multiply by the sample rate. Notice we can only reconstruct frequencies up to half the sample rate. Also notice that we've been assuming that we're sampling and reconstructing with the same sample rate. You can actually reconstruct at a different frequency than what you used for sampling. And earlier versions of musical instruments called samplers use this to change the pitch of sounds. So let's do an example. Here we have a system that's an 11-point averager. Now, a brute force computation of the frequency response would have 11 terms with complex exponentials in them. Fortunately, there is a more compact way to write this with this weird sine over sine function. You can take this on faith for now. We'll talk about where this comes from later. Let's suppose we put in a signal with 2 unit amplitude sinusoids. One has a frequency of 25 Hz, and one has a frequency of 250 Hz with a phase of minus pi over 2. Let's suppose we sample at 1,000 samples per second. The Nyquist rate for the signal, twice the highest frequency, is 500 Hz. 1,000 is strictly greater than 500, so we don't have to worry about aliasing. So we multiply by 2 pi to convert f to omega, and then we divide by the sample rate of 1 kilohertz to put on the hat, yielding omega hats of 0.5 pi and 0.05 pi. And now we look at the frequency response evaluated at 0.5 pi and 0.05 pi in order to figure out what happens to the amplitudes and phases of the sinusoids going through. Notice that no new frequencies are created, and to take the hat back off, we multiply the sample rate, and to express it in hertz, let's divide by 2 pi. So assuming you didn't have to worry about aliasing, the frequencies that came out were the same frequencies that went in. They just have possibly different amplitudes and phases. Just for fun, we're writing this in a slightly different way than we did previously. We wrote it as a cosine with a phase of minus pi over 2, but here we're writing it as a sine. So evaluating the frequency response at 25 and 250 Hz, we wind up with these numbers. So the amplitude of the cosine is going to be 1 times 0.8811, and the amplitude of the second sinusoid is going to be 1 times 0.0909. A phase shift of minus pi over 4 goes here, and a phase shift of minus pi over 2 goes here. Now, we could rewrite this as a cosine, in which case the original phase of minus pi over 2 would combine with this phase shift of minus pi over 2, which would give me a phase of minus pi, which would be equivalent to having a minus cosine form. So the setup is acting like a continuous time, linear time invariant system. If the input frequencies are less than the Nyquist frequency, which is half the sample rate. If you try to put in a frequency that's bigger than that, then you get aliasing, and you've kind of broken the contract. You'll get new frequencies, and it's not an LTI system anymore. So generally, when you build systems like this, you have some sort of analog filter built with things like operational amplifiers and capacitors and resistors in front to make sure that aliasing isn't a problem.